Now, as it happens, the implementation used in our book is actually none of these. We use a very similar approach to 3, I'll call it 3b here, where we leave one empty spot at the front. Okay, so the idea behind this is it just makes the computation of the parents and the children a little nicer, and you use a little extra space. So rather than the parent function looking like this, k minus 1 divided by 2, in this approach, if you leave an empty space, now parent is just k over 2. And that's literally why we do it. Yeah. Seems a little silly, so the authors of the textbook chose to do, but yeah, it does make the math nicer. I'm not going to complain. So in this case, our root is now in position 1, the children are in 2 and 3, and so forth. So if we think about parent, 6 divided by 2, right, that's 3. 7 divided by 2, well, that's 3.5 rounded to down, that's 3 also. Okay, good, seems to work. And left and right child will be similar. And so in next week's lab, you'll actually implement one of these, and you should use this approach in order to understand the textbook approach. Just kind of a nice trick. Okay, it's kind of like a Sentinel node, but in this case, it makes actually it is just like a Sentinel node. It makes the code nicer, but it costs you just a little bit of space. Okay, a message. Okay, so let's now summarize what we know. What we have here is all of the different implementations that we knew about before, that we could have imagined, and here's our new one, a heap. So if we compare it to the others, we can see that it has great performance, but unlike the bushy binary search tree, items that have the same priority are hard to handle. Now, priority, what? Okay, well, this brings us to an important question. Why is this thing called a priority queue? Well, we could think of its position in the tree as its priority. The thing that's at the root is the highest priority item. It's the thing that is going to come out of the priority queue as soon as possible. So if we think about this sock, it's got a bunch of stuff in it. Well, nothing right now, but if I throw a bunch of stuff in it, there's something with the highest priority. It's going to come out of there as soon as possible. So it's like a queue where some people are more important than others. So this is not a very egalitarian data structure. So if you have multiple items of the same priority, let's say you're monitoring the text messages of your citizenry, and two people write equally seditious posts, things we don't approve of, then our bushy binary search tree approach will get confused. However, a heap very naturally handles items with the same priority. For example, an array of all 8s. Now I'll note actually that these approaches here, these runtimes are actually, well, add, this log-in here is amortized because sometimes we'll have resizes. So if we add in a bunch of stuff, there'll be the occasional heap operation where we need to resize our backing array, and that's no big deal. The binary search tree, as it happens, can have a constant get smallest. You can modify this if you keep a pointer to the smallest, so you can modify it if you'd like, but you don't really get much out of it. I'll mention also that array-based heaps, they take a lot less memory, only about a third of the memory, as if we tried to represent our heap with approach 1A. But you could do any of these. Like any of these approaches here will work, but this is the one that we've chosen to use because it uses less memory, is faster, and ultimately has this really simple code. Okay. And just as a follow-on, these heaps here, of course, they handle priorities naturally, as I said out loud, but I guess I'll highlight this bullet point. Same deal. This is just saying the heap needs to have it can have all 8s, and that's fine. So just a couple last implementation questions before we move on. How does a priority queue know how to determine which item is actually larger, like in Java? So if we look at the code here, what would we need to change here? Let's imagine that we wanted to have some default comparison. What we could do is actually go in here and say, we don't just take any item, but we only take items which extend comparable item, basically set here a type bound. And so that right there will now make it so that we can only use our priority queue with comparable items, and there'll be a default behavior. As we did earlier, and you could do that or not, but as we did earlier, we also showed how we could have different orderings, and we could do that by having a constructor in our priority queue implementations. So for example, heap min-pq, where the constructor actually takes a comparator of items. And in that case, it will use the comparator to decide whether to add get smallest or remove smallest. So that's it for the core of the priority queue. From there, you'll implement it on your homework. And I think this is a really nice data structure with a really slick implementation. I love heaps. They're really cool, but they're just not quite as versatile as binary search trees. Nor are priority queues as versatile as maps. And so they don't quite get that level of fame, but they're still very cool and can be very useful indeed.